today I want to talk about conjecture for double twist knots. But I first talk about some memory about continuity integral, and then talk about volume conjectures. And third part is for complexified tetrahedrons. That's a new technique to understand the knot complement. And by using complexified tetrahedrons, I would like to give a proof for volume conjecture of double twist. So first I asked to give a picture of dough, but I don't have any picture, so I just copy the famous paper of dough about the passive knot invariant. Yes, and what I want to say is this paper is received at September 16th of 1999, and around that day, I just visited Max Planck Institute in Bonn. I moved from Princeton to Max Planck at the September of 1992. And at that time, Tanley was there, and luckily, he had this paper at that time. So at that time, there is no, I think, no archive system, not yet, or just beginning of archive system. But I tried to find your paper, this paper in archive, but not in archive there. But Tanley already got this paper, and we read this paper before publishing this paper, and it's very great fun to read this paper. Because I know about something about KG equations. For example, the Corner's work, he used KG equation and iterated integral to make a representation of braid groups. And I also know some work about Greenfeld, about the quasi-triangular quasi-Hopper algebras. Yeah, that paper was first published in Russian, but there is one Japanese mathematician in Russia or former Soviet Union, and he translated the first Russian version to Japanese. And
Tangley speaks Japanese, speaks Russian, right? So Tangley could have read it.
Yeah, but before I met Tanley, I already got the Japanese version of the paper. Yes, but it's a little bit difficult for me. I only understand thing is just the associator, that's the bracket parenthesis operator. That's if associativity is not held, then such a entanglement relation becomes important, but from the Greenfeld paper, I only got such information. But this Dror's paper, it explains everything very clearly, and I actually understand what is the associator for this case. And so then,
now I'm curious, where did Tangley get the paper from? Because indeed, though, it was before internet, right? So
yeah.
Or the internet existed, but there was no
archive system.
Yeah. So I wonder where he got the paper from.
Oh. yeah, that's a mystery. So you. These pictures are obtained from this paper, and this is a very famous formula for iterative integral, and this is how you integrate around the diagrams. And I use such picture many times about explaining this continuity integral. And then associator is given by this N-shaped diagrams, and then this value is given by multiple data values, and then just consider the weight system for continuity integral. So just to apply a representation. So what I did is that associate representation to this sixth strand and consider certain clothing of this n shapes. So closing the n shape, then we get something like this picture. And the continuity integral of this picture is if we apply the weight system, we apply the Lie algebra to this strand, and then it becomes the inverse of the quantum invariant of trivial knot. And so, and the inverse means that the inverse of trivial knot is just inverse of the quantum dimension, and the quantum dimension is given by trigonometric functions. And so inverse of trigonometric function is expanded to Taylor expanded, but the coefficient becomes Bernoulli numbers. And so it gives some relation between multiple data values and some Bernoulli numbers you explain in your talk. Yes. So we get that kind of relations, that kind of values for multiple data values. And I'm very happy to get zeta 2 is pi square over 6 by using quantum invariant. Yes, that's very fun for that time. And then we try to to extend continuity integral to 3 manifold invariant. And then there is a big conference in Oaks at 1995. And at that time, I met Tanley again, and also met Otsuki. Yeah, Otsuki is in Japan, but in Japan, we not so easy to contact because but in that case, it's a good time to discuss with Otsuki and Tanley. So we invented LMO invariant at the time. But at the same time, Dror also worked with Dylan and Rodansky and Stagroff to get the Oaks integral, but we are lucky that we can publish earlier than Oaks integral. Yeah, just lucky, I think. Yes. And this is a very good invariant because it's universal for finite type invariant of 3 manifold and universal for quantum invariant, and it can be generalized to TQFT, and so it can produce the representation of mapping class groups. Yeah, and the basic tool is, as you know, the Jacobi diagrams, which comes from the IHX relation corresponding to Jacobi identities and anti-symmetric relation. That's the bracket is anti-commutative. Yes. But I work for that continuity integral and LMO invariant at this moment, and I found that this invariant is so strong, it contains almost all information about geometry. So without any tools, it's very hard to handle what the meaning of this invariant. So at that time, I just abandoned study about this one. But recently, many tools are invented, and so many things come out from this invariant. It's very happy situation. Yeah. But so I abandoned this continuity invariant, and I switched to the volume conjecture. So what is volume conjecture? That is first conjecture by Lienert, and so he invented new invariant coming from the quantum diagram functions, and so quantum diagram function here we have a pentagon, and we also have five term relation. That's for the quantum diagram. and also by classical dialogue function. Also satisfy these 5-time relations. And so how it relates to pentagons? This 5-term relation gives some basic tool for 3-dimensional PL topology, because if you consider this shape, this is a 2 tetrahedrons, but if you divide it into 3 tetrahedron by considering the faces around this axis. Yes, and this is called 2-3 cardinal moves, and we also have yes 1-4 moves. Yes, both is kind of 5-term relations, and so this 5-term relation gives the fundamentals of the PL topology of 3-dimensional. Yes. And so this invariant comes from these quantum diagram functions, and he also observed that if you take the limit like this way, then it seems to coincide with the hyperbolic volume of the complement of the knot. Okay. Yeah. And he explained this phenomena for figure 8 knot and 5-2 knot and 6-1, but just numerical ones. And so conjecture that this may hold for any hyperbolic knot. And then with Hitoshi Murakami, we found that the Pinat's invariant is equal to the Colored-Jones invariant with corresponding to n-dimensional representation of UQSL2 at the nth root of unity. Yeah, this part I wrote Q equals E2 pi I over n. This 2nth root, but it depends on the conventions. Yes, it's essentially the nth root of unity. Yeah, and then so we propose volume conjecture like this case, and in this case, this volume is Gromov denuded to Gromov's simplicial volume, and so it must hold for any knot, but this just take the complement volume of the complement of, and the complement has some if not complement has a hyperbolic structure, then this gives a hyperbolic volume. But sometimes the complement has split it into some geometric pieces with some part is hyperbolic, but another part is something not hyperbolic. And so this limit just take out the volumes of the hyperbolic part. Yeah. And but so this Colored-Jones invariant is complex numbers. So what about the imaginary part of this invariant? Then we also checked numerically that this imaginary part of this relates to the Chern-Simons invariant of the complement. So yes, and the proof for figure 8 knot is rather easy, but for other cases it's very difficult. And so Otsuki proved for the second case for 5-2, and it's only one knot for about 50 or 70 page paper, yeah, for proving one knot. And he also proved for prime knot up to 7 crossings, and but it's case by case check, and it's very complicated. And then so and but today I want to talk about this when conjecture holds for double twist knot and links. It is in this put it in archive last year. Yeah. Okay. So the strategy of a proof is established by Otsuki. First, replace quantum factorials by quantum diagonal functions, and this is a continuous function. So quantum dialog is a discrete one, but by using quantum dialogues, it becomes continuous functions. And considering the classical limit of such quantum diagonal functions, and we get potential functions. And then we convert the sum to integral by Poisson sum formulas. And then apply the Saddle method, apply Saddle point method to get the actual limit of the invariant. And this last part is very difficult, and just by doing by case check in Otsuki's paper. Yes. What new technique introduced by Otsuki is to use Poisson sum formulas. Before he saying this math, we very naively consider that the sum changes to the integral by Riemann integral. But Riemann integral is not good for such case because this is a very highly oscillating sum. So we have to use Poisson sum formula for this case. And so the potential function uses the first replace quantum diagrams and take the limit. We get the diagonal function like this way, and then the colored zone consists of quantum factorials and some powers of Q, and so the powers of Q part is replaced by some log functions, and then this colored zones explained by something like this form, and here we have n, and this function does not depend on n. And then the good observation is that the value at the saddle point of this potential function, there may be several values. So saddle point means that the derivative for each parameter is 0. But we can find some saddle points that the value at this saddle point will be the hyperbolic volume of the complement. Yes. And this is observed because this equation just coincides with the gluing equation of the knot complements. So I explain this way. So how this saddle point equation corresponds to the gluing equation? So, for colored zones invariant, it comes from the quantum R matrix. And quantum R matrix comes from consists of 5 quantum factorials, and some quantum factorials changed by diagonal functions, and this is explanation of the tetrahedral decomposition of the complement of knot. This we are introduced by Dylan's knot. And so 5 tetrahedrons, and so this complement is decomposed by ideal octahedrons, and each ideal octahedron is split into 5 tetrahedrons, and the third point equation corresponds to the gluing equation around these edges, and so at the total ones, the value of the diagonal function is a little bit different from the volumes, and volume is given by Bloch-Wigner functions. But the difference of values are in total cancelled, and the result will be volume. Yes. So without considering the condition for saddle point method, so applying the saddle point method, it is not clear how it relates to the structure of knot complement and the colored zones invariant by using the potential function. Okay. And so I try to use this correspondence for quantum success symbols. And I want to explain what is quantum success symbol. Quantum success symbol is something we have some representation and C, D, E. This must be a sum of some A, B, C, D, E, F of another switching A, B, C, D, F. This A, B means weight of representations of SL2. And so it's something 1, 2, 3 to 1, 2, 3. Yes. And so so this satisfies also is something corresponding to the making a parenthesis to apply the tensor product of representations. So this quantum success symbol also satisfies this pentagon relation or five-term relation. Looks like this one. Yeah. Yes, if you.
Bidonard-Elliott, no? Bidonard-Elliott identities, no? Bidonard-Elliott.
You have to take some of F. Yeah. Sorry. Yeah. Okay. So for this from this quantum success symbols, I don't want to write down explicit formula for quantum success symbols because it consists of 24 quantum factorials. It's very messy. So if, most people don't like this. But by using quantum success symbols, there is a thrice below invariant for 3 manifolds. This corresponds to the tetrahedral decomposition of 3 manifolds. And so the entanglement relation for the quantum success symbol relate to the 2-3 Pachner moves of this tetrahedral decompositions. And so it must be related to the volume of these tetrahedrons. So I just consider the potential function for quantum success symbol, and then take this other point of this potential function. Then we get the volume formula for hyperbolic tetrahedrons from the quantum success symbols. Yes. And but it does not mean that that certain limit of quantum success symbol coincides with this volume in this setting. Anyway, so and how to prove for the and links for the volume conjecture. So I just follow Oatkins strategy. So use the but. I want to use the expression of Carl-Jones invariant in terms of quantum success symbols instead of the quantum R matrix. So, and so the So if you do these things, then we get some solution for the third point equation, and the parameter corresponds to the edges, but the solution will be usually becomes complex numbers. But usually the edges of tetrahedrons are parameterized by the dihedral angles or edge lengths, and in my formula for hyperbolic tetrahedrons, volume of hyperbolic tetrahedrons, it also works for angles and lengths. But when we consider angle, the angle must be considered as a modulus 1 complex number. And length is considered to be real numbers. But the formula works well for both cases. And this volume formula for hyperbolic tetrahedron is analytic for each parameter for edges, and so it also valid for various kinds of hyperbolic tetrahedrons and also valid for spherical tetrahedrons. So it's very powerful formula. And so, what are the general, for our purpose, the parameter for edges is a complex number, and it's don't correspond to angles or lengths. So how to complexify the parameter at edges? So this is a picture of some generalized tetrahedrons. So usual one is usual tetrahedron like this way, and sometimes the vertex goes to the infinity. And then if some kind of ultra ideal case, the vertex go beyond the infinity, and in that case, three faces, this does not intersect inside the hyperbolic space, but we can get common perpendicular for each edges, and then just cut at this using this common perpendiculars. Then we get such truncated tetrahedrons. And the extremal case is ideal octahedron. The length of edge becomes 0, or a dihedral angle around this edge becomes 0. Then this becomes this extremal case. And then we can also deform like this way. So this is called doubly truncated tetrahedron. But the shape is the same as these truncated tetrahedrons. Yeah. And here is, we start from angle parameters, and it changes to length parameter in this case. And so how to generalize such parameters to complex numbers? So length is just the length of h, but to complexify length, we just look length like this way and twist a little bit by I theta L, just twist. And how to generalize angle parameter theta I for this case? Angle parameter is usually the rotation, but just generalize rotation plus some little shift to this way. This L theta means a little shift for angle parameter. Then we can get this picture. Yeah. And then, and this case, this is twisted, so the faces is no more flat, but we can expect some face along by shifting these edges like this way. Yeah. Yes. And so now I want to explain this complex tetrahedron by using this complex tetrahedron, how the complement of double twist knot is explained. So this is just volumes of such kind of knots, and this explains that this double twist knot comes from the Brownian rings. This expressed like this way, and by putting some surgery along this component, then you get this double twist knot. Okay, and then for Brownian ring case, we consider the elements of fundamental group like this way, and it is this famous fact that the complement of Brownian rings are given by the congruent to ideal regular octahedrons. This gives the structure of complement. We get that if you have two regular octahedron and then identify the faces in certain ways, then you get the Brownian rings. And the observation for this case is that these points are fixed points of such element in the fundamental group, concerning the SL2 or PSL2 representation of the fundamental group and pick up the fixed point for these elements. And then this fixed point gives the vertices of regular octahedrons. And more, this relation is P2 moved by G1, square root of G1, then P2 moves to Q2, this one goes to this one, and this one, I miss, this Q1 goes to P4, I'm sorry, this is Q1, yeah. And so this octahedron and octahedron moved by the square of G1, this gives the fundamental domain of the action of the fundamental group. Okay, so now, so this is a Claude-Jones invariant for the Brownian rings, and the potential function is given like this way. And if you take the saddle point like this values, and then the value at the saddle point is 7.3277. This is just twice of the volumes of the regular octahedron. This is a Brownian case. That's the usual one. But in case of double twist knot, we took the element of fundamental group G1, G2, G3, G4, and G23, G1, 2. This is a new element. So G1, G2, G3, G4 correspond to the meridians, and so the representation of this meridian element is a parabolic element of SL2. But this G12 and G23 is not a parabolic matrix, but loxodromic matrix. It has two eigenvalues, and this eigenvalue consists of some real part and imaginary part. So the absolute real part corresponds to some kind of length, and imaginary part or argument of this correspond to the twist along these ones. And so we can get a picture like this by using the fixed point of this matrix element. So this comes up. And these lines are just drawn by using perpendicular from fixed point P1 to the line Q1, Q1 prime. If the matrix is loxodromic, there is two fixed points on the boundaries, and there is a line which is the axis of the action of the matrix. So and we can draw perpendicular from other fixed point to this line. And then this gives a kind of complexified tetrahedrons. And in this case, we also have the square of such element act just move some fixed point to another fixed point. And so that this one and this one moved by G23 square forms the union of these two complexified tetrahedron forms the fundamental domain of the complement. Okay. So, so this is coming this double twist knot comes from Brownian ring from the surgery. So, and the surgery gives some deformation of the complement, and so along this deformation, this regular octahedron deformed like this way. Okay. And so what about the potential function for this double twist knot? And this part is rather technical, because if you to get the Claude-Jones invariant from this picture, so one way to get the Claude-Jones is just to combine this twist to strands get together, and this part to make it together, and then this part comes from the six symbol coming from this tetrahedral diagrams, and this part represents the twist of this element. But if you substitute the nth root of unity, then that Carl-Jones polynomial becomes 0/0 shape, because if you combine two strings, we have a denominator of quantum integer n. And so this denominator becomes 0 if you substitute nth root of unity. So I apply the L'Hopital's rule for computing these things. But if you differentiate with respect to Q, it is very hard to compute these things. But the Carl-Jones also coincide, this special Carl-Jones coincide with the ADO invariant. ADO invariant is not so popular, I think, but it comes from certain the quantum group at root of unity, and in that case, if you take n-dimensional representation at root of unity, then we can move the weight of representations continuously. And so, by using L'Hopital's rules for to ADO invariant expressions, and then Carl-Jones is given by this formula. Yes. So it has a differential here, but this comes from just L'Hopital's rule. And denominator is just quantum integer, so differential is just constant. So numerator becomes this point. Yes. And then the potential function is this one. Yeah. And the interesting thing about this potential function is that the saddle point for this potential function gives the eigenvalues of this G12 and G23. That is the this logarithmic matrix for this G12 and G23. And so this U and V, this corresponds to the saddle point, but value at the saddle point, and this also corresponds to the eigenvalues of the matrix, and so this actual computation for 6-2. I'm sorry, this is 6, it must be 6-2. Yes, and then it's by using these observations, and so we just get this theorem. Just follow, but this so this just gives the correspondence between the geometric structure of the complement and the saddle point of the potential function. Just this corresponds like this way. But and to prove the volume conjecture, we have to check about the condition for applying saddle point method. That is the last step to consider. And so to do this, it's something messy things. I will skip this one. So this is the picture to explain how to check the condition for saddle point. So we have two parameters corresponding to these potential functions, and so yeah, I have to explain this part because to apply the Poisson sum formula, this sum of integers can be converted to the sum at the integers at the Fourier transform of original functions, and so apply this Poisson sum formulas to this sum. It's converted like this integral and I have to sum over this M1 and M2. I forget to put summation for M1 and M2. This sum corresponds to this one. And then by applying integral by part, yes, I think not so many persons use this integral part in your research, but maybe you teach many times in class. Yes, and so by using integral part, you first integrate this differential part, and then differentiate this part. And so by getting the integral of this part, we have one terms here, and then we have our integral for the differential of this part. But this part is evaluated at the boundary, and value at the boundary is 0. So we can omit this part, and only this part survives. And this is a rather important formula because it has M1, M2 in front. And so if M1 or M2 is 0, this vanishes. So this we call big cancellations because this the most biggest value at this. There are many saddle points, and 0, 0 gives the saddle point at 0, 0 gives the maximal volume. This is just the same as the Bromian case, and the value becomes 7 point something. Yeah, but this doesn't contribute to these summations, and what this is, so if M1 or M2 is 0, we have that large numbers, but this doesn't contribute to the sum, and only M1 and M2 is 1 or minus 1 contribute to the sum. And this, the point at this part just gives the volume of the complement. And so explaining about how this is good for saddle point method. So this is an integral region in the complex 2-dimension. It's a real 4-dimensional space, but the integral domain is 2-dimensional square. So this is picture for real 4-dimensional picture, only like 3D case. But yeah, so this we push this integral domain like this is, and this last part gives the saddle point, actual saddle point for phi. So the integral domain can be pushed like this way, then all values are less than or equal to the volume of this one, and only these volumes contribute to the sum of integrals. And so the volume conjecture actually holds for such cases. And any P and R for any double twist knot, this is P6 and R2 case, but for any P and R, we get this, and so this is volume conjecture. Yeah. So yes, and the last part is just how this volume corresponds to the potential function by. It comes from the Norman-Zagi-Yoshida function to compare the volume and the potential function. Now, so our potential function coming from the Taylor-Jones almost similar to the potential function introduced by Neumann-Zagier, and so the value at the third point also corresponds to the complex volume of the complement. And so that's all for. And have a birthday for draw. Yeah. Thank you.
Any questions?
I just don't understand why the saddle point is the volume. Why the saddle point of solution of saddle point of the potential function is the volume.
Because Neumann-Zagier-Yoshida, there is Neumann-Zagier potential function, and so if you give a surgery along a component, so this double twist knot comes from the third derivative of the Brownian rings. And so in this case, Neumann Zagier used certain formula to express the volume of the complement by using some certain functions. Yes, and this function introduced by Neumann Zagier just coincide with the potential function coming from the colored zones. And by using this correspondence, we can show that the value at the third point is equal to the volume of the complement. This Neumann Zagier used the function is a popular technique in the hyperbolic geometry.
Any other questions?
So volume conjecture for ADO, does it imply volume conjecture for colored zones?
It's me.
If you prove the volume conjecture for ADO invariant,
Oh, yes. And
does it mean that you prove it for colored zones?
yes, so colored, yes, 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 right.
All right, if there's no other questions, let's thank John again.